In the first quarter of 2026, the Linux kernel development process reached a milestone that sounds technical when I first describe it, but that, when you understand what it actually enables, represents a capability that Windows will, for structural reasons rooted in its commercial design, never be able to match. The Linux kernel now supports, as a fully mainlined feature, what the kernel developers call real-time preemption. This has been under development for more than 2 decades. It has been available as a patch set for years. In early 2026, the final pieces were merged, and the mainline Linux kernel, the version that every major distribution ships with, now supports deterministic real-time performance out of the box. If you are thinking, what does that even mean? Stay with me. Because this capability unlocks a category of computing that has, until now, required specialized operating systems, specialized expertise, and specialized hardware. And it unlocks it for free, on standard desktop and laptop hardware, for anyone who wants to use it. Windows cannot do this. Not because Microsoft is incompetent, because the architectural decisions that make Windows what it is are incompatible with what real-time preemption requires. Let me explain what real-time preemption is, why it matters, and why Windows cannot match it. A normal operating system like standard Linux or Windows schedules tasks based on heuristics that balance throughput, responsiveness, and fairness among applications. The scheduler does its best to give each application time on the processor, but the scheduler does not guarantee specific timing. If you have an application that needs to respond to a hardware event within, say, 100 microseconds, you cannot reliably guarantee that response on a standard operating system. Most of the time, the response will happen quickly. Occasionally, because another task is running or a kernel operation is in progress, the response will be delayed by milliseconds or even longer. For most applications, this is fine. For some applications, it is catastrophic. Real-time preemption is a set of kernel changes that, when enabled, gives the operating system the ability to guarantee timing bounds. A well-configured real-time Linux system can reliably respond to events within deterministic time windows, typically measured in tens of microseconds. This is not an average time. It is a guaranteed maximum time. The system promises that under no circumstances will a response take longer than the specified bound. For applications that depend on this guarantee, the capability is transformative. What kinds of applications need this? Audio production, where any timing jitter produces audible artifacts. Video processing, where frame timing must be exact. Industrial automation, where control loops for manufacturing equipment require deterministic response. Scientific instrumentation, where timing of measurements matters. Robotics, where sensor to actuator latency affects behavior. Professional media production, where multiple streams must be synchronized tightly. Gaming, where input to display latency is part of the experience. Each of these domains has, historically, either used specialized real-time operating systems or accepted the compromise of non-deterministic timing. With the mainlining of real-time preemption into the standard Linux kernel, all of these domains can now use standard Linux. Not a customized, specialized, separately licensed real-time Linux. Standard Linux, the same kernel that runs on your desktop, on your laptop, and on the servers powering the internet. Turn on a configuration option, and the kernel gains the ability to guarantee real-time timing. This is significant for several reasons. First, it unifies what used to be fragmented. Previously, a team doing real-time work had to maintain a parallel software stack, with different kernels, different tooling, and different expertise. Now, the same kernel can serve both real-time and general-purpose workloads. Second, it lowers the barrier to entry. Getting real-time performance used to require specialized knowledge and expensive tooling. Now it requires enabling a kernel configuration option. Third, it extends Linux's applicability to domains where it was previously not viable. Industries that required real-time guarantees can now build on standard Linux, which gives them access to the full ecosystem of Linux software, drivers, and community support. Now, why can Windows not do this? The answer is, in part, historical and architectural. The Windows kernel was designed with different priorities than Linux. Windows prioritizes consistency, compatibility, and ease of use for commercial software vendors. The scheduling and timing behavior of Windows is tuned for general-purpose workloads. Microsoft has, over the years, added various mechanisms for applications that need better timing, including multimedia timers, thread priorities, and specific APIs for low-latency work. But these are layered on top of a kernel that was not fundamentally designed for deterministic real-time behavior. The kernel itself retains behaviors, including certain synchronization mechanisms and certain hardware interaction patterns that make deterministic timing guarantees impossible without fundamental redesign. Microsoft has explored real-time capabilities for Windows in various forms. Windows CE, which was used for embedded and industrial applications, had some real-time features, though it has been deprecated for years. Windows IoT has some capabilities. Azure Sphere has more. But these are specialized products, separate from the Windows kernel that runs on desktops and laptops. The core Windows kernel that most users interact with does not have real-time preemption, and adding it would require changes that would disrupt compatibility with existing software, driver models, and application assumptions. The cost for Microsoft would be extraordinary, and the benefit for Microsoft's commercial audience would be small. Linux's situation is different. Linux is an open source project. The developers working on real-time preemption have spent 2 decades addressing every architectural obstacle. They have rewritten scheduling, synchronization, and timing primitives. They have worked with hardware vendors to ensure that the capabilities are supported by modern processors. They have done this work in public, with community review, without commercial deadlines. The work could take as long as it took because there was no shareholder pressure to ship it by a specific date. The work could be as thorough as it needed to be because the developers had the freedom to make the right choices rather than the expedient ones. This kind of patient, open, technically ambitious work is not impossible in a commercial context, but it is rare. Microsoft, facing the pressure of quarterly earnings and commercial priorities, does not have the luxury of a 20-year mainlining project for a specialty feature. What does this mean for users? For most desktop users, in the immediate term, it means nothing. You are not doing audio production, industrial control, or scientific instrumentation. Your computer works fine with standard scheduling. Real-time preemption is a capability you can turn on if you need it, and if you do not need it, it is invisible to you. For users in the domains that benefit, this is a transformation. Audio producers can use Linux for professional work with better timing guarantees than most proprietary audio operating systems offer. Video editors get tighter frame timing. Industrial users can standardize on a single operating system across their entire stack. Scientific instruments can run on standard hardware with real-time drivers. The ecosystem of what Linux can do expands meaningfully. For the broader technology industry, the implications are several. Linux's applicability has expanded again. Open source software has demonstrated, once more, that patient community development can produce capabilities that proprietary alternatives cannot match. The gap between what Linux offers and what Windows offers has widened in a specific, consequential way. For industries considering what operating system to standardize on, the list of capabilities where Linux has an advantage is longer. There are caveats. Enabling real-time preemption has performance implications. A system configured for real-time behavior does not perform as well on throughput-oriented workloads as a system configured for general-purpose use. The trade-off is real, and for most desktop users, the standard kernel is the right choice. Real-time preemption is for the specific applications that need it, not a universal upgrade. Real-time performance also depends on hardware. A poorly designed system can have latency sources that the operating system cannot overcome. Properly configured hardware with certified real-time drivers is needed to take full advantage of the kernel capability. For serious real-time work, hardware selection matters, and the real-time patches still require configuration. Enabling real-time preemption is a configuration option, not the default on most distributions. Users who want to take advantage of it need to either build a kernel with the option enabled or use a distribution that ships with it on. Several distributions now offer real-time kernel options, and this will expand as the capability becomes better known. The broader observation I want to make is that this is an example of how open source development works when it is done well. The real-time work on Linux has been led by a small number of engineers, many of them employees of companies that use Linux commercially. Some of them volunteer community members over a very long period. The work has been reviewed, tested, and debated in public. It has survived decades of criticism and setbacks. The result is a capability that is genuinely excellent, genuinely world-class, and genuinely available to anyone who wants to use it. This kind of outcome is hard to achieve in a proprietary commercial context. Companies face pressures to ship, to monetize, to retire investments that are not paying off on commercial timelines. Open source, when well-funded and well-directed, can escape those pressures, and the results, over long time scales, can be astonishing. Real-time preemption is one such result. It took 20 years. It is now available to everyone. The gap between Linux and Windows, in terms of raw capability, is now larger than it was a year ago. The specific gap I described today is just one example. Comparable gaps exist in areas like file system flexibility, container support, networking capabilities, and several others. These gaps do not matter to most users, who will never need the capabilities in question, but they matter cumulatively. The operating system that supports more capabilities is, for organizations and users who find themselves at the edge of what is possible, the stronger platform. If you are doing serious technical work that butts up against the limits of what Windows can do, Linux is now, measurably and specifically, a better tool. The examples I gave: audio production, video processing, industrial automation, scientific instrumentation, are the visible ones. There are others. The long tail of Linux's capabilities extends further than most Windows users realize, and the gap is widening, not narrowing. Subscribe for the next video, which covers the specific configuration steps to enable and tune the real-time Linux kernel, including distribution recommendations, hardware considerations, and the benchmarks that demonstrate the capability in action. And in the comments, tell me whether real-time computing is relevant to anything you work on, and whether the mainlining of this feature changes your assessment of whether Linux is the right tool for your use case. I am interested in hearing specific examples, because the theoretical capability is less interesting than what people actually do with it.